Okay. Okay, so basically the idea from the last portion is that, given a matrix A, you construct n Gershkovin circles, one corresponding to each row, and the eigenvalues will lie on that. Now, what is so special about rows here? Why can't we do it for columns? Right? So if you draw the Gershkovin circle for the columns, that is as if you're drawing it for the rows of A transpose, is it not? Okay, so the thing is that A and A transpose share eigenvalues, right? Have the same set of eigenvalues. Okay, we know this. I think we referred to this before. If A is symmetric, it's a no-brainer because A and A transpose are equal. But even if not, you are saying that they share the same set of eigenvalues. That's because the characteristic polynomial will be the same, right? For 2 cross 2 matrices, you know that trace and determinant of both the matrix and the transpose are the same anyway, right? Other than that, you can also look at it from the definition, right? So if you do lambda I minus A transpose, that's like writing det of lambda I minus A whole transpose. Okay, and the determinant doesn't change when you take the transpose, right? So you simply get det of lambda I minus A. Okay, so A and A transpose have the same set of eigenvalues. So basically, by applying the Gershkovin circle theorem to A transpose, okay, apply circle theorem to A transpose, sometimes can give you maybe better better estimates on the eigenvalues, because the circles will change, the radiuses will change if you actually change the rows or the columns. Okay, so basically you can draw 2n circles, right? You can draw one circle for each row, that's n circles overall, and one circle for each column, that's n circles, total 2n circles, right? You can draw 2n circles and you will say that any eigenvalue lies in one of these circles. That's perfectly valid. Okay, so you can either draw it for the rows or for the columns. Okay, so that may give you better estimates for the eigenvalues. Okay, you can actually do something even stronger. You can take any matrix S and consider SA S inverse. Okay, so I might remind you that SA inverse and A share eigenvalues. It doesn't matter what S is, right? SA inverse and A share the same eigenvalues. It's because when you try to compute the the characteristic polynomial of SA S inverse, right? So SA S inverse, right? You can just write it, use the following analysis. So you can just write I here as S times S inverse, right? So det S S inverse minus SA S inverse. Okay, so S here is some n cross n square invertible matrix. Okay, so that's going to be determinant of S times lambda I minus A times S inverse. Okay, now because determinant is just multiplicative, this is going to give you det S times det lambda I minus A times det S inverse. Okay, but det S times det S inverse is 1, right? So these two terms might as well be removed because their product is 1. So you are left with simply the characteristic polynomial of A. Okay, so basically this matrix over here and A share the same characteristic polynomial, and therefore they have the same eigenvalues. Okay, so I can pick any arbitrary S, compute SA S inverse, okay, and then draw the circles for SA S inverse. As you can see, maybe this will give me even better information. Of course, the cost of computing these matrices itself is going to be very high, but it's particularly useful when S is diagonal. Okay, so pick S to be diagonal. If you pick S to be diagonal, like S is let me call it D, to emphasize that it's diagonal. So S is like D, and that is D1, D2, so on up to Dn. The diagonal entries are just all the off diagonal entries are 0, D1, D2 to Dn. So what happens when you do DA D inverse, right? So what happens when you have a matrix A? So let's take the simple 2 cross 2 case, right? So A is like a 2 cross 2 matrix, A11, A12, A21, A22, and you multiply it with DA D inverses, D1 0 0 D2 and D1 1 by D1, so that's D1 inverse, okay, 1 by D1 0 0 1 by D2. I'm just trying to compute this product here for the 2 by 2 case. Okay, so what will that be? It will just be, well, when you multiply, D1 multiplies with A11 here, right, and D1 will multiply with this, Okay, when you multiply with 1 by d1, that will cancel. So I'll leave it as an exercise for you to just finish off this algebra and check that the diagonal entries will not change actually. They'll just be a11 and a12, but the off diagonal entries will change. It will be like a12 times d1 by d2, right? And this will be a21 times d2 by d1. Okay, that's what it will look like. Okay. So leave it as an exercise and feel free to correct me later if I am wrong. But this is what the matrix is going to look like. Okay. And you're free to pick d1 and d2. It doesn't matter what d1 and d2 you pick, the eigenvalues don't change. Right? That's the beauty of it. So maybe I can pick d1 and d2 in such a way that the circles look a lot simpler, or they'll give you a lot more information about the matrix than otherwise. Okay, let me take an example. So let's take this A to be this matrix, right? 1, 2, 1, 1, 0, 2. This example is from your textbooks. I'm just lifting that example directly, right? So A equal to 1, 1, 0, 2. This is my matrix. I know what the eigenvalues are, correct? It's an upper triangular matrix. The eigenvalues are simply 1 and 2, right? I think in the earlier example I had somehow put a -1 here. That's not there now. So it's simple to see that the eigenvalues are just 1 and 2. Okay, so let's draw the Gershgorin circles for this, right? So if you draw them, so the first circle is going to have center 1 and radius 1. Okay, so like before, so maybe the center is here, the radius is 1, so it's going to look something like this. Okay, this is going to be the first circle, right? And the second circle is going to have center 2 and radius 0. Okay, meaning it's just going to be this dot over here. Okay, so this is 1 and this is 2. So this is my first circle and this is my second circle. Okay, first circle is like, circle, real circle. The second circle is a degenerate kind of circle, just a dot. It's a radius 0 circle. Okay, fine. So these are the Gershgorin circles. Now they tell me precisely what this eigenvalue. So it doesn't actually tell you exactly what the eigenvalues are. Okay, it doesn't actually exactly tell you. It tells you that the eigenvalues are going to be in this disk. It's actually a very big disk, right? It doesn't really help us much in this context. Okay, but suppose I pick D to be like maybe 100, 0, 0, 1. Let me check if that's the correct thing to pick. Pick D to be like 1 by 10, 0, 0, 1, something like this. Okay, fine. So let's say I pick D to be this. Okay, so in other words, from this example here, D1 is this one, 1 by 10, and D2 is 1. Okay, and let me construct DAD inverse. Okay, so what is DAD inverse going to be? If you look at this expression over here, DAD inverse is going to be again 1, 2 in the diagonal, but this entry becomes 1 over 100. Okay, because D1 is 1 by 10 and D2 is 10. D2 is 1 over 10, sorry. This becomes 1 over 10, right? And this entry is 0 anyway, so that doesn't change. Okay, now if you draw the Gershgorin circle for this matrix, okay, now you can see that the circle is going to be centered at 1. Okay, so let me draw the Gershgorin circle for this matrix in a different color. Centered at 1 and radius of 1 by 10. Okay, so it's going to be a much smaller circle, something like this. Okay, and the other Gershgorin circle is going to be centered at 2 and radius 0 as before. That doesn't change. So the second Gershgorin circle is going to be here. So for this matrix, the Gershgorin circles are these two. Okay, and as you can see now, if I try to conclude something about the eigenvalues of this matrix, it's much more precise. We'll say that the eigenvalue is close to 1 within 1 by 10, right? And second, so you can readily say that the eigenvalues are, so there is a lot more precision in the information that you are giving about the eigenvalues. Okay, earlier you were saying eigenvalues are in this full area, and you are saying they are only in this small area or here. Okay, so the uncertainty in your information about the eigenvalues has drastically reduced by actually doing this. Of course, nothing is stopping you from picking 1 by 100 here, in which case the radius will be even smaller. Okay, of course beforehand you will not know which D to pick. In this case I know because I constructed my matrix A like that. Beforehand you will not know which D to pick, right? So you'll have to fool around a bit and check how it will work. So computationally it's still not very efficient, because you may have to search many different Ds before you find one that actually gives you better information about the eigenvalues. Okay, so in general also, even when you don't have 2 cross 2 but maybe 3 cross 3 or n cross n matrices, the same thing will happen, right? So you'll get A11 here, you'll get A12 d1 by d2, you will get A12 d1 by A13 d1 by d3, and so on. Okay, so this dA d inverse will be a matrix with same diagonal entries as A, but the off diagonal entries will be multiplied with reciprocals of the entries of capital D, the matrix capital D. Okay, fine. So this is a useful trick to apply to sometimes reduce the radii of these circles. Okay, fine. So that's the main idea behind the Gershgorn circle theorem. You just identify the circles or rough regions in which the eigenvalues lie, and hopefully this gives you information about the spectral radius of the matrix. Very useful application of the circle theorem is to something called diagonally dominant matrices. Okay, this is what I was bringing up in the very beginning of this lecture. Okay, so diagonally dominant matrix is a matrix in which the diagonal entries are very large, but the off diagonal entries are all collectively very small compared to the diagonal entry. That's what a diagonally dominant matrix is. And the idea is that using the Gershgorn circle theorem, you can say that for a diagonally dominant matrix, the eigenvalues may be close to the diagonals or something like that. Okay, let's look at precise definition. This definition is again motivated from the circle theorem. Okay, so we say matrix is diagonally dominant if the absolute value of the diagonal entry is bigger than the sum of all the absolute values of the off diagonal entries, okay, in any row. Okay, so j not equal to I for any I. Okay, meaning that in the matrix, no matter which row you pick, right, the diagonal entry will have an absolute value that is larger than sum of all the absolute values of the others combined. So this is precisely your Ri from the Gershgorn circle theorem, the ith radius. Okay, so what does this say, right? I mean, thinking intuitively from the complex plane perspective, it says that your ith diagonal entry is very far. Okay, the distance of the ith diagonal entry from the origin, this is what this is bigger than the radius of the circle. Okay, that means maybe your ith diagonal entry is here and your radius is, something like this. Oh, sorry, something like this. Okay, or maybe your ith diagonal entry is here, in which, if it happens to be negative, but your radius will be something like this. Okay, in any case, your radius, which is this distance, will be smaller than the distance from the origin of the center itself. Okay, so with this definition, if a matrix satisfies this, we say it's diagonally dominant. And what is the immediate consequence of a diagonally dominant matrix? The immediate consequence is, one, that none of the Gershgorn circles, none of the circles, okay, include the origin. Okay, so it doesn't matter whether your diagonal entry is positive or whether your diagonal entry is negative, because the radius is smaller than the distance, your circle will never actually hit the origin or include the origin for that matter. Okay, any circle, all the circles will stay away from the origin. Okay, what that means? That means that 0 is not an eigenvalue of such a matrix. Okay, of a diagonally dominant matrix. 0 is not an eigenvalue of a diagonally dominant matrix, right? In particular, that means that any diagonally dominant matrix is invertible. Okay, any diagonally dominant matrix is invertible. You can see that it is extremely simple coming from the circle theorem. Okay, by the way, this if you're given this and asked you to prove this, you would have used exactly the same techniques as you used in the proof of the Gershgorn circle theorem, right? You would construct an x such that ax equal to 0 and try to apply absolute values and see if it works out or not. Okay, it's precisely what you did in the proof of the Gershgorin circle theorem also. Anyway, so that's the main idea. Any diagonally dominant matrix is invertible. Okay. By the way, for the purpose of this lecture, the entries of the matrix also could be complex. Even then the theorem will go through, right? For example, this AII, for us matrices are all real, right? I mean, that's the assumption we started with in this course. Even if they are not, the circle theorem will apply exactly in the same form. Okay. The statement will basically AII, if it is complex, well, then it's going to be located somewhere away from the real axis, right? Somewhere here or here. Even then, if the radius is bigger, the radius is smaller than the distance to the origin, then the same thing happens, right? The circle doesn't include the origin. Okay, fine. So this is one very important consequence of the circle theorem. Another consequence you can immediately say, so suppose A is diagonally dominant. By the way, there are other definitions of diagonal dominance as well, but this definition makes sense in the context of the circle theorem, right? Suppose A is diagonally dominant with positive diagonal entries. With positive diagonal entries. So diagonal entries are all positive, right? So AII here will always be positive. So what that means is this situation will not arise for us. Only these situations. Circles will only be located on the right half plane. Okay. So basically this situation will not arise. So let me just cut it out. The situation will not arise. So you'll only have these kind of situations. Okay. So circles will all be in the right. So if you draw the other circles, maybe they'll look like this, maybe like this or whatever. But they'll all be on the right hand side. Okay. Suppose A is diagonally dominant with positive diagonal entries. Okay. A is, let me also put in symmetric here. Suppose A is symmetric, diagonally dominant with positive diagonal entries. Okay. Symmetric also means that the eigenvalues are all going to be real. So for sure they're going to lie on the real axis. Okay. Okay. So what does this mean, right? Diagonal dominance ensures that none of these circles reach the origin. Okay. The diagonal entries being positive ensures that they all stay to the right, to the left. Okay. What these two ensure is that all eigenvalues of A are positive. Okay. In other words, A is positive definite. Okay. The matrix is positive definite. So you can see that it's actually very interesting. Okay, that if you actually somehow end up with a matrix that is diagonally dominant, okay, symmetric, and the diagonal entries are all positive, then it's positive definite. Okay, extremely straightforward. See, this check, by the way, you would have done anyway, right? So remember from our earlier discussion, we said if a matrix is positive definite, then diagonal entries have to be positive. Okay, we discussed this before. Right? So this anyway had to be true. Symmetric anyway we restrict only to symmetric. We are saying if you have diagonal dominance, then positive definiteness follows. Okay. Converse may not be true. Okay, you may have a matrix that is positive definite but not diagonally dominant as well. Okay, very good. Okay, so there are many variants of this, but let's actually jump ahead to some very concrete applications, right? So I'll discuss two matrices or two categories of matrices which I'm going to prove are positive definite using the circle theorem. Okay, or I'm going to prove some property of these matrices using the circle theorem. First is what is called the Laplacian matrix. If you've been reading your book, you might have come across this matrix quite a bit already. If not, well, here is the definition of a Laplacian. So in a Laplacian matrix, is going to be a square matrix, n cross n matrix. All the entries of Laplacian matrix are integers. Okay. Okay. So the diagonal entries of this matrix are going to be some integer, positive integers. Okay. So maybe this diagonal entry is 5. This diagonal entry is like 3. This diagonal entry is, so let me just draw for the sake of simplicity. Let me just take, this diagonal entry being 2. This diagonal entry is 1. Maybe this diagonal entry is also 1. Okay, they're going to be integers. Okay, and the off diagonal entries, okay, so diagonal are positive, diagonal are non-negative, can be 0 also, right? Off diagonal are 0 or minus 1. Okay, and the number of off diagonal entries will be such that there will be as many minus 1s as the diagonal entries. For example, this row has 2, right? So this row must have 2 minus 1s. So minus 1 and minus 1 like this. Okay. This row only has 1 here. Okay. By the way, this matrix will also be symmetric. Also has to be symmetric. So a bunch of rules here, right? Too many rules, correct? Yeah. So because of symmetry, this entry is forced to be minus 1. Okay. Now in this row, the diagonal entry is only 1, so you're only supposed to have 1 minus 1. You cannot have more than that. So this entry is forced to be 0. Okay. This entry is forced to be 0. By symmetry, this is also forced to be 0. And this entry is minus 1. By symmetry, this is also forced to be minus 1. And that works for this 1 and minus 1. Okay. This also means that the diagonal entries cannot be very arbitrary. Okay. For example, I could not have put a diagonal entry of 5 here like I was initially doing. If it is a 3x3 matrix, the diagonal entry can be at most 2. Okay. So why are Laplacian matrices important? They arise when you study graphs. Okay. So if a 3x3 Laplacian matrix corresponds to a 3-node graph. Okay, so graph is basically, a set of nodes and connections that are called edges, right? All of you have come across graphs in some context or the other, right? So here you have node 1, node 2, node 3. So let's say this row corresponds to node 1, this row corresponds to node 2, this row corresponds to node 3. Okay, so in a Laplacian matrix, the minus 1s denote the edges. So this entry is minus 1, means that there is an edge between node 1 and node 2. Okay, because this is precisely the 1-2th entries of the matrix. Okay, so let's say this is node 1, this is node 2, this is node 3. There is an edge between node 1 and node 2. That's what this minus 1 says. This minus 1 says there is an edge between node 1 and node 3. Okay, so there is an edge here. Okay. This 0 says there is no edge between node 2 and node 3. Okay, there is no edge here. So this is the graph that you are studying. Okay, and Laplacian matrices arise naturally in the context of graphs. Okay, I will not go through in detail here because that's not the subject of our course, but needless to say, it's actually very important to check if this matrix is positive definite or positive semi-definite or not. Okay, because a lot of properties of the graph rely on quadratic forms associated with the Laplacian. Okay, in the eigenvalues of the Laplacian. Okay, so how do we check if this matrix is positive semi-definite or not? Well, by the very definition I gave you, right? You can very easily see that this matrix, the Laplacian, satisfies aii, it's always positive, bigger than summation of absolute value of aij. Sorry, equal to, that's what I mean, equal to aij, j equal to 1 to n, j not equal to n. Okay, we can see the very definition I gave, right? I said, well, there has to be as many minus 1s as the diagonal entry. That means what? That means that the diagonal entry is actually equal to the sum of the absolute values of the half diagonal entries. 2 is equal to 1 plus 1. Right? Similarly, 1 is equal to 1 plus 0, and this 1 is equal to 1 plus 0. Okay, so the diagonal entry is actually equal to the sum of the half diagonal entries. In other words, aii is equal to ri in this case. Okay. So what will happen when you draw the Gershgorin circles? Right? When you draw the Gershgorin circles, okay, every Gershgorin circle, let's say this is the center, then the radius will actually be equal to this distance. The radius will be equal to this distance. That means the Gershgorin circle will certainly pass through the origin, will certainly hit the origin, like this. Okay. Well, hopefully. Okay, somehow that worked. Yeah, it's better. Okay, so the Gershgorin circle is going to look like this. A different Gershgorin circle, maybe for a different row, the aii will be different, and the Gershgorin circle will look, something like this. Okay, and so on. So all the Gershgorin circles are going to be of this type. Okay, so you can have this as another Gershgorin circle, for example, for a different radius. So this is how the circles will look like. Right now, what does this matrix is symmetric? So you know that all the eigenvalues lie in this region now. In particular, this region is to the right of the imaginary axis, meaning that all the eigenvalues will be greater than or equal to 0. Okay, because the Gershgorin circles do not include any portion on the negative side. Okay, That's it, very simple. It says that all the eigenvalues are greater than or equal to 0. Now, of course, in general, there is a much easier proof. There's a much, I wouldn't say easier, but more relevant proof, more relevant to graphs, I mean, to show that, this matrix is positive definite. You can construct the quadratic form and show using that. Okay. But in this context, it's actually extremely simple, right? So you'll just look at the Gershkovin circles, look at the geometry of them, right? They're all to the right, and so all the eigenvalues are greater than or equal to 0. Okay? Fantastic. I'll discuss another category of matrices, and in fact here it doesn't matter, very interestingly, what the graph is, right? The structure of this matrix and the graph doesn't matter, right? This could be an arbitrary n cross n matrix with, as long as it satisfies this rule, right? Then you are done. Okay. I'm going to discuss stochastic matrices next. Okay. So a stochastic matrix is an n cross n matrix. We briefly sort of defined this in one of the exams in the first segment, if I remember correctly. But let us just redo the definition anyway, right? A stochastic matrix is an n cross n matrix, not necessarily symmetric. Unlike Laplacian, which is symmetric, may not be symmetric. Okay, may not be symmetric, but it's a matrix that always has entries. Okay, the entries of this matrix correspond to probabilities, basically, right? So let's say it's a 2 cross 2 matrix. Simply, each row is going to correspond to probabilities that sum to 1. Okay, for example, this entry could be like 0.1 and this entry could be 0.9. Okay, and this entry could be like 0.2 and this entry 0.8. So basically the row sum is 1. Okay, the row sum is 1. That's what it says. That's the stochastic matrix, right? So basically all entries between 0 and 1, okay, and entries in a row sum to 1. Entries in any row sum to 1. Okay, so Laplacian arises when we study graphs. Stochastic matrices arise when we study Markov chains. Okay, so what are Markov chains? Essentially, they are like probabilistic random processes. So, they're random process. Let's take a simple scenario, right? So let's say that you are trying to model the weather in your town. Okay, very simplistic example that I'm taking, right? And suppose that very simply your weather can either be sunny or it can be cloudy. There are only two possibilities for your weather, sunny or cloudy. Okay, very simplistic model, right? And there is a transition model, meaning that suppose if the weather today is sunny, it could get cloudy tomorrow with a probability of 0.1. Okay, right? Or it could stay sunny with a probability of 0.9. Okay, so this is how you will draw this. Again, this is a bit rushed, just to give you a very quick flavor of this, right? And if the weather is cloudy today, it could get sunny tomorrow, represented by this arrow, with a probability of 0.2. Okay, or it will stay cloudy. Okay, so I think let me just modify these things a bit. So I'll call this 0.9, this 0.1. Okay, so basically if your weather is sunny today, it's going to become cloudy with 90% chance tomorrow. It's a very weird model. I should have picked better numbers here. But if it's sunny, it could become cloudy with probability 0.5. So effectively this row corresponds to sunny, this corresponds to cloudy, this column corresponds to sunny, and this column corresponds to cloudy. Okay, this entry represents the probability of the weather staying sunny if it is sunny now. Okay, so that's this arc basically, right? The weather is sunny now, the probability will stay sunny tomorrow also. That's this entry. This entry is sunny now, cloudy tomorrow. Okay, so sunny now, cloudy tomorrow. That's 0.9 probability. Okay, okay. Similarly, if the weather is cloudy today, with 0.2 probability it becomes sunny. Okay, and with 0.8 probability it stays cloudy. Okay, so somehow the city has predisposition towards cloudy weather, it would seem, right? It's very likely to be cloudy all the time. Anyway, fine. So that's the model here. Okay, simplistically. So when we study Markov chains like this, right? So when you have these things are called states. Okay, and these are called state transitions. Okay, when you move from one state to the other with probabilities. Okay, that's when you get this stochastic matrix, something called a stochastic matrix, right? All of you get an intuition of why the rows have to sum to 1, right? Because rows represent all the possibilities. If it is sunny today, it's either sunny tomorrow or cloudy tomorrow. So one of these two has to be true, right? That means these probabilities have to sum to 1 on any row. Okay, that's basically what's going on at a very, very coarse level. Okay, it turns out that it's the powers of this matrix. Let's call this matrix as P. The powers of this matrix are very useful to predict the weather. So let's say P to the 3 will be useful to predict the weather 3 days from now. Okay, P square will be useful to predict the weather 2 days from now, and P to the 4 will be useful to predict the weather 4 days from now. So in general, you are actually going to be interested in matrix powers, P to the n. Okay, as they happen, and anything to do with matrix powers, we know that the spectral radius is a very important component, right? So you want to know that the spectral radius is less than 1 for these matrices, okay, for things to make sense eventually. Okay, so we need some estimate of spectral radius of such matrices, correct? So that's where I'm going to insert the Gershgorin theorem, circle theorem, right? So what happens when we draw the Gershgorin circles of such a matrix? Okay, so the radius is going to be these, right? 0.1 and 0.8. So the radius will be AI. First of all, you note that these matrices are not symmetric. They are not diagonally dominant. This example that I have here is very clear that in this entry, in this row, the off diagonal entry is much bigger than the diagonal entry. Okay, so they are certainly not diagonally dominant, certainly not symmetric also, right? So the eigenvalues could be complex in general, right? So let's take Gershgorin circle, center AII. Okay, so the center will actually be the diagonal entries. The diagonal entries are going to be between 0 and 1. Okay, so you know for sure that the center is going to be on the real axis somewhere between 0 and 1 AII. What is the radius? Okay, so the radius Ri is going to be 1 minus AII. Okay, I would leave this once again as an exercise for you guys to check. It's very simple, right? Because all the off diagonal entries are positive, right? So the absolute value doesn't make sense to me. I can just get rid of it because they're all positive or non-negative anyway. So I'm just going to sum all the off diagonal entries. But if I sum all the off diagonal entries, I should get 1 minus the diagonal entry because the whole row must sum to 1. Okay? So Ri must be 1 minus AI. So basically what you have here is a setting in which the centers are like AII, okay, and the radius is like 1 minus AII. Okay, so this AII is always going to be between 0 and 1. Okay, the radius is going to be 1 minus AII. Okay, so AII is always going to be between 0 and 1. So let's take an example, right? So let's say AII is like 0.75. Okay, 0.75. So this distance is like 0.75, right? Then what is the radius? Radius is going to be 0.25. So if you draw the circle, you will actually get it to be like this, something like this. Okay. Or you could have AII close to 0, like, maybe 0.25. Okay, in which case what is the radius? The radius Ri is going to be 0.75. Okay, so in that case the circle is going to actually include some negative portion and it's actually going to look something like this. Okay, this not to scale, just rough diagrams. Okay, so in any case you see that the worst scenario for you is when AII is close to 0, in which case the radius is 1. Okay, so let's draw the worst and the best cases in some sense. Okay, so if AII is 0, then the radius is going to be 1 and your circle is going to look something like this. Okay, so this is 0, this is minus 1, this is 1. This is the scenario when AII is 0. Okay, when AII is 1, the circle is going to look like this. When AII is 1, the circle is just going to be this one. Okay, because the radius is going to be 0, right? So it's just going to be that dot, degenerate circle again. Okay, you can see by sweeping AII through all these regions, you can see that you can never actually get the circle to go beyond this interval. Okay, whatever circle you draw, okay, it's going to be within this. The largest possible circle is this one. Okay, this has the highest radius, right? For the radius to be highest, AII has to be 0. So this is the largest possible circle. The smallest possible circle is this one. Okay, and every other circle is going to be somewhere in between. Okay, so none of these circles will have a portion that's beyond 1 or below minus 1. Okay, so in particular, all the circles are going to be lying in between these two. So it will lie in this slab. The circles will all lie in this slab. Okay, and that means that all the eigenvalues are going to be less than 1 for sure. Okay, the absolute value of all the eigenvalues will be less than 1 for sure. Okay, to be precise, I should say less than or equal to 1. Okay, the less than or equal to 1, the equal to 1 will happen if you have a 0 diagonal entry. Okay, if in this matrix you end up having a 0 diagonal entry, right, that will actually bring this big circle into play. Otherwise, it won't even touch -1. Okay, it could touch 1, however. Okay, when will it touch 1 here? It will touch 1 provided, so when will you get this dot over here? You will get this dot provided one of the diagonal entries is 1, ai is 1. Okay, so you can see that no matter what the scenario, the rho is going to be less than or equal to 1. So in other words, the spectral radius is always going to be less than or equal to 1 for this matrix. Okay, which is a very useful property to have. Okay. So we didn't say spectral radius less than 1, we said less than or equal to 1. Okay, fine. So that is yet another application of the Kirchhoff circle theorem.